Today we're going to be discussing effect size, and specifically we're going to be talking about effect size for one-way ANOVAs. So as a reminder, effect size is the magnitude of an effect treatment independent of sample size. To look at that graphically, here is an image from your book. So in the first graph on the top, we have the distribution of SAT scores before treatment and a distribution in the blue dotted line of SAT scores after treatment. Presumably the treatment is some sort of SAT training course. And we do see an increase in the difference in the mean of the population. We have a mean of 500 for before and a mean of 515 afterwards. We have then an effect score between those two of 0.15. Cohen's d is 0.15. Again, those distributions are pretty close to each other. They're pretty much on top of each other. When we're looking at the graph below, the distribution of IQ scores before treatment and the distribution of IQ scores after treatment, those distributions have a much larger effect. That treatment has a much larger effect. And so here we have an example where we have a Cohen's d of 1. Again, there's not as much overlap between those distributions. This should look familiar from when we talked about alpha, beta, power, and effect size. These distributions over each other. So once again, let's kind of review alpha, beta, power, and its relationship to effect size because they all work together. So in the distribution on the left, we have the distribution where we fail to reject the null and the results are inconclusive. And the distribution on the right side of the line, we have reject the null and support the research. One of them is the comparison distribution and one of them is the research distribution. In this situation, we have the mean of distribution 1 is greater than the mean of distribution 2. So this is our comparison distribution, population 2, and it's everything under that curve there. So we have, again, that's our comparison distribution. And then we have our distribution of means, our population 1. These are the means when the research hypothesis is true. Again, we're doing null hypothesis testing. So our comparison distribution is the idea that there is that the null hypothesis is true, that there is no effect. So again, that's the difference between the two distributions again. So again, everything under this curve is that distribution of means, the means when the research hypothesis is true. The difference in means between the two is our effect size. So just like we saw in that previous graph, the difference in the means, say on the distributions between the SAT scores of 500 and 515, translated to the Cohen's d. We use that then to calculate d. The same is true here. So we have a effect size that's a little bit larger in this distribution. The cutoff value is then again set by us. We get to decide what level of risk are we going to have to commit this type of error. So our alpha level is set on the comparison distribution. So we're saying there's a 5% chance or a 1% chance that we're willing to commit this kind of error. By setting alpha, we set beta on the distribution of means and the distribution where our research hypothesis is true. And remember, power is everything outside of beta on that distribution. So by setting that cutoff of alpha, beta and power are determined. With a fairly large effect size, that's not very big of a deal. Again, we have a fairly large effect size here. These distributions aren't very much on top of each other. There's not a lot of overlap. So we still maintain a lot of power. But if you look at it, again, an example where we have a much smaller distribution, again, between a much smaller effect size between our two distributions, our comparison distribution and our distribution of means, here we have a much smaller effect size between those two, the difference. There's a lot more overlap between these two distributions. When that effect size is a lot smaller, we can set that alpha at the exact same level, but look how much more beta we have. Look how much more risk we have of that type 2 error. And subsequently, look how reduced our power is. So again, there is this relationship, and effect size is not necessarily determined, but is influences how these type 1 and type 2 errors and our power play out. So again, as alpha increases, beta decreases. When alpha decreases, beta increases. That's again just what we saw in those previous slides. As you increase alpha to a higher level, we reduce our risk of, reduce beta, which is those type 2 errors. When we decrease alpha and we make it smaller and smaller, so say we go from 0.05 to 0.01, we increase beta. Again, beta is that risk of missing that effect. And the relationship between power and effect size is when you lower the risk of the type 2 error, so again from 0.05 to 0.01, the risk of missing an effect, which is beta, decreases. The risk of increases and power decreases. So as we lower alpha, as we lower that, we reduce our risk of a type 1 error. But we increase beta, which is our risk of a type 2 error. By increasing beta, we lower power. And again, it's just a trade-off between the two types of mistakes. And effect size plays a role in this. If you have a really large effect size, it's not that big of a deal because you're still going to maintain a lot of power. If you have a very small effect size and those distributions are quite on top of each other, it really could create a situation where you, again, have a type 2 error, you miss that effect that's actually there. So it's important to kind of understand effect size of the phenomenon that we're studying. So here are those exact same kinds of graphs pulled apart instead of on top of each other. Instead of physically on top of each other, I've pulled them apart so you can see, again, by setting alpha at 0.05, we set beta on that distribution of means, and then power is subsequently set from that. So how do we measure effect size for Anova? We're computing a percentage of variance accounted for by the treatment conditions. And in published reports of Anova, we usually use eta squared to explain this. Just like it was with R squared, we're talking about the proportion of variance explained. It's very similar kind of ratio here. So we're not using Cohen's d for Anovas, but it is still a measure of effect size. And how we calculate that is we calculate the between treatments, sums of squared between treatments over sums of squared total. Remember, our sums of squared between treatments is going to have what in it? Is it going to be primarily noise, or is it going to be signal and noise? The answer should have been signal and noise. We're looking at the difference between our treatments. That's where our signal is going to be. And then we divide it by the sums of squared total, which has all of our noise and all of our treatment effect. So from the example from our criminal record study that we've done previously, we had sums of squared between as 43.33, and we had sums of squared total as 107.33. If you again go back and look at that example, you'll see those are the values that we came up with. You just do the ratio of those two, so 43.33 divided by 107.33, and we get an eta squared of 0.4. This is the proportion of variance explained by the treatment conditions. So it is, again, telling us about effect size. Another example, the temperature memory study, which is an example for you to work through today. We have sums of squared between, sums of squared total. We have eta squares at 0.65. Again, this is the proportions and variance explained. We're going to be using these in our F statements. So when we talked about F statements last time, we left out one piece of it, and this is the piece that we left out because we hadn't gotten to effect size yet. So we're going to include the F in degrees of freedom like we talked about, the p-value, and eta squared. Again, I like to include mean squared error as well because you can build back that entire F table, those entire Anova tables from that F statement if you're including the mean squared error, the mean squared within in that. But if you have an effect, if you are able to reject the null, you need to be including eta squared. If you don't reject the null, you don't need to include eta squared because there's no effect, just as the way we saw in t-tests. So again, that's that last piece of that APA style F statement. Please go back and look at the examples that we've done previously in class and online that we asked you to do an Anova on, and go back and calculate for the studies that we were able to reject the null. Go ahead and calculate those effect size, that eta squared, so we get some practice doing that. We will see you in class on Wednesday.